All right, guys, so today we are on 5.3, and we're talking about inverse trig functions. So just a quick review to what you did last year. Remember, an inverse trig function, when you're taking a regular trig function, if I'm taking the sine of some angle, the sine of, let's say, 50 degrees, my answer is some ratio, okay? Some ratio A over B. When I'm taking the inverse trig function, when I'm taking the inverse sine, I don't know what my angle is, okay? I don't know what my angle is. So when I take the inverse sine, instead of an angle being after this inverse, my ratio is going to follow my inverse, and I'm going to have my angle as my answer, okay? So a normal trig function gives you a ratio of the sides. An inverse trig function tells you what angle has that ratio, okay? So a couple of things to remember, and I know we're kind of going fast through these. We'll cover it a little bit more in class if we need to. We do have some limitations on our domain. So when I'm working with inverse sine, my domain goes from negative pi halves to positive pi halves. So really, when I'm dealing with inverse sine, when I'm dealing with those y values, I'm only working between what it means by negative pi halves. Pi halves is up here, right? Negative pi halves is that same distance in the other direction. So negative pi halves is right here. So 3 pi halves and negative pi halves are the same thing. So when I'm looking for these values using inverse sine, I'm only looking at numbers, at angles in between here. There's going to be lots of them. There's going to be, an infinite number of answers. So we limit that to only between negative pi halves and pi halves. When I'm working with cosine, I work from 0 up to pi, okay? So when I'm working with cosine, I'm working with angles from 0 to pi. And when I'm working with tangent, again, I go from pi halves to negative pi halves. So it's the same as my sine function. And really what we're looking for is we want the chance to get a positive degree and a negative degree. And that's why we limit the domains the way that we do. So let's just look at a few of these. Like I said, I know we're going quick. Maybe I'll leave that negative pi halves right there. And we're going to kind of do the same thing with the degrees. When this right here, 11 pi sixths, is the same thing as going pi 6, but in the negative direction. So instead of 11 pi 6, we can call that negative pi over 6. And 7 pi fourths is the same as pi fourths. So we can call that negative pi fourths because we're going down that same length. And then this would also be negative pi thirds. So that's kind of what we're going to use on our inverses. A couple of other things that you're seeing a little bit different here. If you notice that up here on the top, it's using sine raised to the -1 as a notation for inverse. You'll also see arc sine. That means the same thing. They just write it two different ways depending on the book, depending on the author, depending on the paper. It's the same thing, it's just two different notations for it, all right? So when it's asking me to find the arc sine of -1/2, what it's asking me is what angle gives me a sine of 1/2. Okay, so what do I know about sine? I know that sine is my y value. So if I start looking at my unit circle, I'm looking for a y value of -1/2. So going up, none of these are going to have y values of -1/2 because the y values are positive. So I'm looking down here at these three, and I've got a -1/2 right here. Now, we erased this. That angle is 11 pi sixths. But because that's not in my domain, remember, we're going to call that negative pi over 6 because 11 pi sixths is not in our domain. So I would say that my answer to that would be negative pi over 6 because that is the y value that gives me negative 1/2 as an answer. We could also say negative 30 degrees depending on how we're working with this, okay? If we're using this in calculus or if we're using this in something else, at some point you might want to actually use the degree form. Okay, arc sine of 2. So again, I'm using sine, so I'm going from pi halves to negative pi halves, and I'm looking for a y value. What angle gives me a y value of 2? Well, going back to trig, we know that our domain, our outputs for sine are always between negative 1 and 1. So no angle is going to give me a sine of 2. It's undefined. That doesn't exist. Okay, I can't take the arc sine of 2 because no angle gives me a sine of 2. All right, so looking at arc cosine of root 2 over 2. So cosine are my x values. So this is asking me what angle gives me a cosine of root 2 over 2. What is that angle? Now cosine, remember, we go from 0 to pi so that we get positives and negatives, and I'm looking for a positive root 2 over 2. So I look at my x values. Root 3 over 2, root 2 over 2 is that one right there. So I would say pi fourths is the arc cosine of root 2 over 2. That is the angle that gives me root 2 over 2. Arc cosine of negative 1. So again, cosine is my x values. So I'm looking for an x value of negative 1. And since cosine goes from 0 to pi, negative 1 is going to happen right here at pi. So my answer for that one would just be pi. Now tangent's a little bit different. Our sine and our cosine can't go out of the bounds of negative 1 and 1, but tangent can be a lot of different things. So even though it says negative 8.45, I'm not worried because that's normal for a tangent function. Now this one obviously is not a pretty number. So this one we're going to actually do on the calculator. So if I graph this, what's going to be our fastest way? Because we have our inverse, if I just inverse tangent, so on your sine, cosine, tangent buttons, you have the regular sine, cosine, tangent, but above them in blue, you have the inverse. So if it says tan to the negative 1, that's my arc tangent, and I want negative 8.45. And it's going to give me an answer of negative 1.453. Okay, so what that looks like, if you look at the tangent graph, if I just do tangent of x, notice how it just keeps repeating, right? Our sine and cosine look a little bit different. Our sine is a wave. So if I graph my sine, I get this wave, and it stops. It only goes up to 1, and it only goes down to negative 1. But my tangent graph goes up to infinity. So tangents can have any value as an output. So we don't have that same limitation like we do on sine and cosine. So going back to my problem, negative 8.45, my angle is going to equal, it was negative 1.453. Now make sure I don't double check enough on here because I don't really use my calculator on here for anything but calculus. But when you go to on your mode, you need to make sure that you're in radian mode, okay? Make sure you're not in degrees, otherwise that tangent's going to give you, this says negative 1.453 radians, which is what we use in calculus, so we're going to make sure to put it in radian mode. Okay, moving on. So these inverse trig functions, these are our last transcendental functions. So we're not going to take the time to walk through these proofs too much, but I did want to put them on here for you to see. If I have y equals the inverse sine of x, then what that means is sine of y equals x. And I drew a picture for you right here. So sine of some angle, so right here's my angle, is equal to x, which means my opposite over hypotenuse is equal to x. So that means my opposite is x, my hypotenuse is 1. And if I use my Pythagorean theorem, I find out that that means my adjacent is root 1 minus x squared. So that's what the triangle is showing you. It's just showing you the picture of what's going on in this problem. So if I take the derivative of sine y equals x, I get cosine y dy dx is equal to 1. And then if I get my dy dx by itself, dy dx equals 1 over cosine of y. And we know that the cosine of y, cosine, remember, is, I'm using my angle y right here. That's a terrible color to use, right? I'm using my angle, and cosine is adjacent over hypotenuse. So cosine is adjacent over hypotenuse. So that's why cosine changes to root 1 minus x squared. Anyway, we don't need to worry about proving them. They're actually pretty easy to prove with the picture. They're a little bit harder to do if you don't draw the picture first. So if you ever forget what these are, you can always draw the picture and figure it out that way. But these are ones that we want to memorize, okay? These are ones that you want to have in your bag of memorized formulas, especially because I'm not going to remember them. So we're going to rely on you guys to do a little bit better at that. So putting these into use, all right? This wants us to solve without using a calculator. So it wants me to take the tangent of the arc cosine of 3/4. Now this actually works because when I take the arc cosine of 3/4, that's going to give me an angle. My answer to the inside is going to be an angle. And then I'm going to take the tangent of that angle. First thing I need to do is figure out what my angle is. So the way I like to do these is I draw a triangle, and I don't know what the angle is. So I'm just going to put my symbol in there. But I do know that the cosine of my angle is 3/4. Okay, the arc cosine 3/4 means that the cosine of some angle is 3/4. So that means my adjacent is 3 and my hypotenuse is 4. So if we do a little bit of Pythagorean, so 3 squared plus x squared, well, not plus, is going to equal, what, 4 squared? So 9 plus x squared equals 16, so x squared equals 7. So x equals root 7. All right, so this is going to be root 7 right here. That's my third side. Now going from there, I still don't know what my angle is, but I don't need to know what my angle is because I'm just taking the tangent of that angle. Well, tangent is just opposite over adjacent. Remember SOHCAHTOA, tangent's opposite over adjacent. So this is my angle. Whoops. This is my angle. The opposite is root 7. The adjacent is 3. So my answer is just root 7 over 3. That becomes my final answer. So you're actually using tangent, and you're using regular trig functions, and you're using inverse trig functions at the same time. So just be careful setting up your triangle. On this second one, cosine of some angle, we don't know what the angle is, but it wants me to take the inverse sine of negative 2/3. Now, a lot of people panic when they see a negative on the inside, because how do you draw a triangle with a negative side? Well, really it doesn't matter because it's going to go away when we use the Pythagorean theorem. But basically I have an angle and my sides, the ratio, remember sine is opposite over hypotenuse. So my opposite, there's a 2. My hypotenuse, there's a 3. Now, if I'm doing this correctly, that 2 is actually a negative 2. So my triangle is actually going down, right? My 3's right here. My 2's going down. If I was looking at this like the unit circle, your hypotenuse is never negative. The negative always goes with the other side. So to take the cosine of this, I need to know my adjacent side. So again, Pythagorean theorem, negative 2 squared plus some number squared equals 3 squared. So 4 plus some number squared equals 9. So some number squared equals 5. So some number equals root 5, right? So this becomes root 5. So now I can just take the cosine of my angle. Again, I still don't know what my angle is, but I don't need to know what the angle is. I'm looking for the cosine of my angle, and cosine is adjacent over hypotenuse. So I get root 5 over 3. So when you're taking a trig function, when you're using a trig function and combining that with the inverses, just be careful. You don't need the calculator. You could put this in the calculator. You'll get the same thing. But make sure that you know how to do these without that calculator as well. Whoops. Okay, moving on. So here's a few more derivatives of these trig functions. Again, this is probably something that you want to have memorized. We're going to start doing quizzes on this here in the next couple of weeks. But the derivative of arc sine or sine inverse of u is u prime over root 1 minus u squared. Okay, cosine is over here on the right. Tangent, notice that sine and cosine are almost exactly the same. The only difference is the u prime on top becomes negative. And that's the same with cosecant and secant. Secant is a positive u prime. Cosecant is a negative u prime. Other than that, the bottoms match on those derivatives. So for now, have these written down, but they're ones that you're going to want to start working on having memorized. Okay, so putting this into use a little bit. Let's try and get a good range here. So the derivative of arc sine of 5x. Now I just took these same functions up here, these formulas, and I just copied them over here on the right. So these on the right, don't get confused by those. Those are just the formulas we're going to use. So the derivative of the arc sine 5x. Well, my formula tells me that my derivative is u prime over root 1 minus u squared, okay? And u is just whatever follows my sine. So in this case, my u is 5x. So that means my u prime is just 5. So I can just plug that information into my formula, okay? U prime goes on top, so 5 goes on top. On the bottom, I need square root 1 minus u squared. So 1 minus 5x squared. So when I simplify, 5 over root 1 minus 25x squared. Okay, don't forget to distribute that square to the 5 and the x. Again, if this was free response, that top answer would be just fine. Multiple choice, you might need to switch it over to that bottom one, all right? Okay, second one, derivative of 4 arc tan of x over 2. That 4 is just kind of floating out in front, right? So it's kind of like I put the 4 out here in front of my arc tan formula. Other than that, it's just u prime over 1 plus u squared. So u is right there. So my u equals x over 2. That's the same thing as 1/2 x, which is how I prefer to write it. So I'm going to leave it that way. So the derivative of 1/2 x, that goes on top. That's just 1/2 over 1 plus u squared. Well, u is this, So I'm going to put 1/2 x squared. And when I simplify, oh, I'm not done. There's a 4 out in front. Don't forget that 4. That's going to change our problem. So 4 times 1/2, that becomes 2 over 1 plus 1/2 x squared becomes 1/4 x squared. Once you distribute that square to everything, right? So be careful of that 4. I almost forgot that that was floating around in front. Don't forget that one. And then on the multiple choice, I'm guessing that this is probably not going to be one of the options because of that. You have a fraction inside a fraction. They don't usually like that. So on the multiple choice, I would times the top and the bottom by 4 to get rid of that fraction. So then you just end up with 8 over 4 plus x squared. Because that 4 on the bottom cancels with the 4th, and it just makes it look a little bit nicer. So multiple choice, that's probably going to be your answer right there. Free response, though, you could leave it clear up here in this form, and you'd have the right answer. As long as the numbers are correct, you'd have the right answer, okay? All right, the derivative of inverse secant of e to the 3x. So inverse secant, now that I've scribbled all around it, is right here. U prime over absolute value of u, root u squared minus 1. So first things first, u equals e to the 3x. And I like to write these first just because I'm going to plug them in my formula, and then I know that I have them right. So my u is the derivative of that, which is just, or my u prime, which is just 3e to the 3x. So when I plug those into my formula, u prime goes on top, so 3e to the 3x is going to go on top. On the bottom, I'm going to take the absolute value of u, which was e to the 3x, and then I need a square root, and then I need u squared, so e to the 3x squared minus 1. And let's clean this up a little bit. The e to the 3x and e to the 3x are going to cancel out, so I'm left with 3 on top. I still have my root on bottom. That 2 distributes, right? Well, I know I say distribute, but you've got to, that 2 is going in, and when you're taking a exponent and you're raising it to another exponent, you're actually multiplying. So that becomes e to the 6x, because I do 3x times 2, not 3x squared. And then I still have a minus 1 floating around. And that's as clean as it's going to get unless you rationalize the denominator, but I would start with that unless it wants you to simplify further and you don't have a choice. But if you have a choice, leave it right there where it is. Okay, now integrals. These ones are a little bit messier. I know there's a lot of stuff to memorize today. Going backwards, these aren't something that we're going to prove today. Maybe in the future we'll have some time to do that. Today it's just formulas that we're looking at, okay? So the integral of 1 over root a squared minus u squared. So if I have something, and I'm going to rewrite this just a little bit. I'm going to rewrite this as the integral of 1 over root a squared minus u squared, and then my du. Because the derivative is not always right on top, right? If you see something in this form with an a and a u squared on the bottom underneath the root, then that gives you a hint that this is your integral, okay? If you see something that has a squared plus u squared on the bottom, then your integral is going to be a arctangent. If you see u root u squared minus a squared, then you get this arcsecant as your integral. Again, not ones that you're going to want to have to prove. They're ones that you're going to want to memorize, okay? And these ones don't tend to surprise you. For example, looking at this integral right here, a lot of times you have a hint that you're using an inverse trig function. So you know that you're looking for this pattern rather than just having to come up with, oh, I recognize out of my 100 integrals that I've memorized, I recognize that one as the arc sine. That's going to be a little bit harder to do. You usually have a little bit of help knowing that you're looking for a trig function. So what I'm looking at here is arc sine. So this looks like the first one because on top I have a du. In this case, it's dx. On the bottom, I have root a squared. In this case, a is 3 because 3 squared is equal to 9 minus a u squared. Be careful here because u is actually 2x. Because if I square 2x, I end up with 4x squared. So I have an a and a u, and all I have to do is plug them into this nice, wonderful arc sine formula. So my integral becomes arc sine. U goes on top, so 2x is going to go on top. On the bottom is going to be a, which is just 3. And don't forget the plus c, because this is an indefinite integral, right? I don't have bounds on my integral. Okay, this second one, there's not a square root, so I'm probably not using arc sine or arc secant, but the bottom technically could still look like my arc tangent one. I have something squared plus something else squared. In this case, something squared is equal to 3. Well, that makes a equal to the square root of 3. And something squared is equal to 16x squared. So my u is going to be 4x. And then I get to plug it into that wonderful formula. So 1 over a is just root 3. Arc tangent. U goes on top, so 4x over root 3 plus c. This one would be a lot more difficult to rationalize because this one in front wouldn't be. I could just multiply by root 3 all the way across. But to get rid of that root 3 on the bottom is going to be a big ugly mess, and we're not even going to try because that's not what we're doing today. So this would be my final answer. 1 over root 3, arc tangent 4x over root 3 plus c. Just don't forget that plus c. So on your homework today, you're going to be looking for some patterns, okay? This is your hint. We are doing arc functions right now. We're doing inverse trig functions. So these are patterns that you're going to be seeing. If it wants you to take the integral of something, it's going to be one of these 3 because those are the 3 that we taught you, okay? So if it's asking you to take an integral, look at these 3 and find the one that matches, find your bottom that matches, okay? If you're doing derivatives, you've got your functions right here. Okay, so memorize them if you can. If it's not, that might take you some time. So for now, they will be up on the board in class, and you can, you've got your notes, so go ahead and use your notes. But this is, so what are we on? Homework 5.3. And we'll go over questions in class and talk a little bit more about this as well.